Hi, kiddos. Today we're going to talk about something called linearization. And it's one of those things in calculus that is just so easy that it's easy to overthink. So I want to start by showing you what we're doing before we do it, because the how is pretty easy and the why is also pretty easy. So what's about to happen is we're going to take some ridiculous curves. Like this is a ridiculous curve. But the point of linearization is you're in calculus now, so everything happens at an instant in time. There's instantaneous rates of change. So what's going to happen is we're going to zoom in on a point somewhere along this ridiculous curve. And what's going to happen is as we zoom in, so I'm looking at this peak right here, like that's where it's the curviest, in my opinion. So if I'm looking at this peak and I zoom in on it, as I get closer, closer, instantaneously close, like all the way close, it starts to turn linear. It becomes less curvy. The closer you get to it, the more linear it becomes. That's called having local linearity. So at that instant, local to it, it is becoming more and more linear. And I mean, we can do this all day long. Is it ever going to go completely straight? No, obviously not. And we're zoomed way in. So that's why taking a derivative and doing a tangent line works. Like that's why all of this works, is because curves at a point are linear. As opposed to this guy, we're down here at this corner. I can scroll in for a while and it never flattens, it never starts to turn linear, it never even curves a little bit. So this point down here does not have local linearity. That's one of the reasons why we can't take a derivative there. And that's one of the reasons why it's non-differentiable at that point. All right, so now that you have seen again that different curves turn linear at points, we're going to do this thing called linearization. Linearization is an approximation technique. So you're going to use this to approximate different values of a function. All right, let me draw a quick squiggle wiggle for you to show you how it's come. There's my squiggly wiggly. I'm going to call it F, and you're going to need, I mean, we're writing lines, right? I mean, linearization, line is right in it. So we're going to write lines. I'm going to put a point right here that I'm going to call A. This is going to be a known point. I know where that is. It's at A, F of A. I know that value, F of A, got it, no problem. Linearization says, okay, but what if I need this function value? And I know it's X value. I know it's a little bit further away. I know it's close to A, but not all the way. Like it's not A, it's just close. What we're going to do is we're going to take this tangent line at the point we know, and we're going to use that tangent line to approximate this function value. So my green dot's too big. It's blocking my view. We're looking for this green dot value. Instead, we're going to end up finding this function value. And we're going to say, close enough, good enough, because the tangent line sits close to the curve as long as your values are close together. So that's what we're doing. Everything is just a tangent line today. So I'm going to give you, I think we'll do two. And the first one I'm just going to make up. It's going to be so good. So I'm going to say use the line, the tangent line, to some function that I am inventing on the spot. I want to throw a sine. Oh, I'll do a sine inverse because who cares? We'll do that. Use the tangent line to that curve at x equals 0 to approximate f of 0.2. So the first thing is that it's important that the point you know and the point you're looking for are close together. And I know it's all relative, like 0.2 might be a big thing in some worlds, but right now those are close enough together that our tangent line is going to be a good representation, a good approximation technique. So we're going to start by only reading this much of the question because I could have asked you that on any of your last 2 or 3 tests. We're going to write a tangent line to that curve at the point x equals 0. Got it. No problem. To write a tangent line, you need a point and you need a slope. So I'll do the point first. X is 0. Y is going to be inverse sine of 0 plus 4 times 0. Do I have to write it? Maybe I do. So 0, inverse sine of 0 is 0. So this is just 0, 0. Our slope is going to be a derivative. So I need f prime of x. The derivative of inverse sine is root 1 over 1 minus x squared plus 8x. And then I need to evaluate that at 0. I don't want the derivative everywhere. I want the derivative at our x value. So this is going to be 1 over 1 minus 0. So 1 plus 0 is 1. This is the most boring line of all time. But I'm going to be thorough. Like I'm going to write everything, even though it feels weird. I'm going to do y minus 0 equals slope x minus 0. And I'm going to leave that. And I'm sorry if that hurts you, but I'm going to leave it. That is this much of the question. But now we're supposed to use this line that's so pretty and uncomfortable because I have zeros everywhere to approximate this function value. So please know, we all know this is an x value because it's inside. I'm going to take that x value and put it where x is, and that's going to approximate my function at that point. So I'm not plugging. I mean, in a normal world, you would take 0.2 and you would just put it in here, right? And you would pull out your calculator and you would just give me the actual answer. And I know that about you, and that's fine, and that's okay. And I'll tell you why we're not doing that when I can think for a second, because I can't think and write at the same time. This is just 0.2. It's boring, but it's fine. Okay, the reason we're not doing that is because this technique gets used a lot when you have incomplete data. So perhaps you don't actually have the function. Maybe you just have a table of values. And so you can't just plug it in and see what the calculator says. We're practicing with actual functions because I want you to practice taking derivatives because you have a test. So that's the only reason I'm doing them this way. I think your book asks them this way as well. Let's do one more. Would you please go with me to approximate the square root of 4.01? Same question. We're going to use a tangent line. This time the information's just not laid out for you as nicely as I wrote it out in the first one. So you're going to have to go find some things. Like 4.01 is the value you're trying to use to approximate. So you need a number that's close. I pick 4. 4 is close to 4.01, so I'm going to use that as my known value. The function I think I might ought to use is square root of x. So if I use those two things and I write a tangent line with that information, my point is going to be 4.2. My slope is going to be 1 over 2 root x, such that x is 4, gives me 1/4. So my tangent line is y minus 2 equals m, x minus 4. Great. Now I want to go put into x the x I'm looking for, which is 4.01. Please don't put the square root of 4.01 in. The explanation as to why is just as simple as this is what you're using and this is what you got. So I'll write it. I feel silly doing it, but I'm doing it. If I need to know what x is, I can square root both sides, or I can square both sides. So 4.01 equals x. So that's the x I'm going to use. Okay. So if I plugger that in and I get y equals 1/4 times 0.01 plus 2, because I went ahead and added that 2 to the other side, and that equals 801 over 400. Trust me. I like these questions. I hope you like them too, simply because it's easy to see if you did something terribly wrong. Like the answer should be close to the point that you know. The whole purpose of using lines, the tangent lines, is that they should always be close. So my answer is a little bit more than 2. That feels good. Let me show you this one. I put this one on Desmos too as well. So the red is the square root function. The blue is the tangent line, and then I just plotted that point for you so you could see. We're going to zoom. We're going to zoom, and we're going to zoom, and we're going to zoom. This is the 0.42. The point that we're trying to approximate is over here at 4.01. And can you see that the tangent line and the graph are so close together? I can't even tell them apart right here. Like I see over here red and blue, but these guys are almost literally on top of each other. Even as I zoom in closer, 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 I can't distinguish between them. So that's why this is used as an approximation technique. I hope that was the easiest video you've ever watched. Let me know if you need anything.